So let's think about this. Which of the following cations have no effect on the pH of a solution? Potassium ion, iron 2 ion, or aluminum ion? Well, if we think about, these are the parents, they're cations, so we got to think about what compound they make with their base. So KOH, FeOH2, and aluminum hydroxide, AlOH3. Are any of these strong? Well, certainly we need to recognize that KOH is strong. Therefore, no effect on the pH. And then we have our other two, and these are not strong, not necessarily weak bases, but they are not strong enough to, they will affect the pH, and when they undergo hydrolysis, it will make the solution more acidic. And this is happening by, when it's undergoing hydrolysis, we're removing hydroxide and converting them into the hydronium ions. So that makes, on the number line, if you think that the hydronium ions, adding that makes it more acidic, makes it decrease on the number line. More acidic is my lower numbers as opposed to having a more basic solution. So this is kind of a summary page here, looking at the combined effect of our cations and our anions in solution. So an anion that is a conjugate base of a strong acid will not affect the pH. And if we think back and recall, and we just talked about our 7 strong acids. But if we think about those conjugate bases, for example, we know that we have hydrochloric acid, so the Cl- would be the conjugate base of that. This will not, chloride will not affect the pH. Same with bromide from hydrobromic acid. Same with iodide from hydroiodic acid. Same with ClO3- chlorate. Same with perchloric, ClO4-. Same with nitrate from nitric acid, NO3-. And same with HSO4 from our sulfuric acid. We have HSO4. 1, 2, 3, 4, 5, 6, 7. These 7 conjugate bases will not affect the pH. There's a whole lot of other last names out there, a whole lot of other bases that will affect the pH, but these 7 will not. An anion that's a conjugate base of a weak acid. So all of the other last names that are not these, all of the other conjugate bases, those negative anions, will cause the pH to increase. Okay, that means it's becoming more basic or less acidic, or the number on the pH scale is going up. Remember, the highest is 14, so it's going to cause that pH to increase in number. And finally, a cation that is the conjugate acid of a weak base will cause the pH to decrease. And if we think back just a couple slides ago, our strong bases, we had our cations, which include lithium, sodium, potassium, rubidium, cesium, calcium, strontium, barium. These are all the cations of strong bases that will not affect the pH. Okay, these are all other cations, a cation that is the conjugate acid of a weak base, will cause the pH to decrease. Every other cation that is the conjugate acid of a weak base will cause that pH to decrease, meaning it's going to become more acidic. So we were just, ammonia, we just talked about that one just a little bit ago. We have ammonium, NH4 plus. So we have ammonium, our cation, and its conjugate base is a weak base. Ammonia is a weak base. So this cation that's from a weak base is going to make our H3O pluses. This is going to make our solution more acidic, right? When it goes through hydrolysis and we have hydronium ions coming out of the solution. And just to hammer it home, the cations of group 1A are sodium, potassium, lithium, strontium that we just listed in the last slide. And our group 2A, the calcium, strontium, barium, will not affect the pH because they are the cations, or positive cations, of the strong Arrhenius bases. Again, all of the other metal ions will cause a decrease in pH, making them more acidic. So let's say a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base. The ion that has the larger equilibrium constant, whether that's Ka or Kb, will have the greater influence on the pH. So if Ka is greater, it's acidic. If Kb is greater, it's basic. And if they are indeed equal to one another, it's neutral. And if you think about that, remember back that Ka times Kb is equal to Kw. So if they are equal, they would have to both be 1 times 10 to the negative 7th to give us our neutral water K constant. So let's take a peek at an example. All right, let's look at a problem here. List the following solutions in order of increasing pH. So we have barium acetate. So we have barium, let's write Ba barium. Acetate is C2H3O2. So we have barium, Ba2 plus, and we know that this parent base would be barium hydroxide. And we have talked about many, many, many times about how this is a strong base. It's not going to have an effect on the pH. But let's look at acetate. When we have C2H3O2 minus, we know acetate's parent acid, so this is my parent base, which is the barium hydroxide, and we know that that's strong. Acetate's parent acid is acetic acid, HC2H3O2. We know acetic acid is weak, and it will affect the pH. It will undergo hydrolysis. And if you think back to what that looks like, if I have C2H3O2, let's do it up here. C2H3O2 undergoing hydrolysis. Then we have the acetate grabbing a hydrogen to make its parent acid, which is acetic acid, HC2H3O2, and that leaves this water with OH minus. ions. That makes it more basic. So this is going to become more basic. So this barium we're not taking into consideration. It's the acetate that is going to go through hydrolysis and make this more basic. Let's look at ammonium chloride. Ammonium chloride is, let's go over here, NH4Cl. And if I look at ammonium, so let's look at just NH4 plus. So let's look at its parent base. Its parent base would be NH3, ammonia, which is weak. And when ammonia goes through hydrolysis, let's look what that looks like. And when NH4 plus goes through hydrolysis, NH4 plus forms its parent, we just said ammonia, NH3, it loses a proton, and so then therefore water becomes H3O plus, so it's going to make this more acidic. Okay, so we know on our number line so far, increasing order of pH. So a low pH means more acidic, which so far, this one is going to be lower, more acidic. It'll be on the left side of our number line. And we said that barium acetate is going to become more basic. It's going to be on the right side of our number line so far. And then if we look at the second part, so we looked at the ammonium, now let's look at the chloride, Cl minus. Its parent acid is HCl, which we know is strong, part of that strong 7, so there will be no effect on the pH. So we've got more acidic here, we've got more basic here. Let's look at our next one, our methylamine bromide, and it gave us our formula here for methylamine bromide. So let's split this apart into its NH3CH3, our methylamine, and then our bromide, our Br minus. Well, first, the Br stands out to me because we know that its parent acid, is HBr, hydrobromic acid, which we know is strong, which will have no effect on that pH. So let's see if this methylamine does. Methylamine, if its parent base is NH2CH3, this is the parent base. And if you aren't sure about what that is, we haven't seen this one before. But if you look at our Appendix D, we can see on here that methylamine, CH3NH2, has a Kb constant. And we know that every base that's listed on our Appendix D is a weak base. Every acid on our Appendix D that has a Ka constant is a weak acid. So the fact that it's listed on here is telling us that it's a weak base. So therefore, we know that when this undergoes hydrolysis, when the weak base undergoes hydrolysis, when this undergoes hydrolysis, it is going to produce more H3O positive plus ions, which is going to make this more acidic. Similar to this, remember when I had my NH4 added to water, so we had then its parent base and hydronium. So if I took NH3 and CH3 plus water, so it's undergoing hydrolysis, it's going to make this parent base and hydronium ions. So this one is also going to become more acidic. So we're going to have to compare this methylamine bromide and ammonium chloride because we said both of these are going to be more acidic. Let's look at potassium nitrate first, and then we'll come back to that one. So, potassium, KNO3. So we know that K, its parent base is KOH. I guess I didn't need the parentheses. We know this is strong. NO3, its parent acid is HNO3. We know this is nitric acid. We know that that's strong. Both of these will have no effect on that changing that pH. And when you have a strong acid and a strong base and it creates our salt in our water, we end up having a neutral solution. So now let's look at our options here. I'm going to turn this page around here so we can kind of make our number line. We have more acidic, we have more basic, and so far we know that our barium acetate is going to be most basic of the four of these. So this is our Ba C2H3O22. And then we have our in between more basic, more acidic, we'll say put our neutral, which we said was our KNO3. But now we have to decide the difference between ammonium chloride and methylamine bromide. So let's compare their KBs. The KB of NH3, and let's look at the KB of NH2CH3. So I'm going to get my appendix D out here. My base of ammonia, 1.8 times 10 to the negative 5. And my KB for methylamine, 4.4 times 10 to the negative 4th. So we can do one of two things. If we look at the KB values, we know that the greater the KB, the more basic it is. So which one of these is the greater number? Well, the number that's to the negative 4th is a greater number. Negative 5 is a smaller number. So if this is a greater KB, that means that this one is more basic, which means on our number line, it's not going to be further left, it's going to be further right. So we would say our methylamine bromide, NH3CH3Br, and then therefore, since this one's more basic, this one's got to be more acidic. Our ammonium chloride would be the most acidic. So this would be 1, 2, 3, and then 4. We also could, if we were thinking more acidic, we could look at the Ka values of these, and to find the Ka values, we would just do Kw, which is 1.0 times 10 to the negative 14th, divided by the Kb value, divided by Kb, that's equal to the Kas. And again, the larger the Ka, the more acidic it is. So if we did 1 times 10 to the 14th divided by 1.8 times 10 to the negative 5, we would get 5.56 times 10 to the negative 10th for our Ka. And let's just write that over here to the side. Our Ka would be 5.56 times 10 to the negative 10th. And if I did the same thing for my Kb value, and I found the Ka, so again, 1 times 10 to the negative 14th divided by the Kb value here, I would get 2.27 times 10 to the negative 11. So which value is greater? Well, in this case, this value is greater. So it's telling me it's more acidic, right? A value to the negative 10 is a larger number than that to the negative 11. So it's telling us the same thing we just found. Here, this compound is more basic. It has a higher number. This is more acidic. It has a lower number. So that was just kind of double confirming. Let's look at this one. In each of the following, indicate which salt will form the more acidic solution. So we have sodium nitrate or iron 3 nitrate. So let's write these down. Number 1, NaNO3 versus FeNO3. Okay, so let's think of this. Let's look at, we both have nitrates in common. And those are my bases. So let's think about its conjugate acid in both situations, which would be HNO3. Its parent acid, we know that nitric acid is strong, right? That it is not going to have any effect on the pH. So let's just cross those off. Now we just need to compare our cations, sodium versus iron. So let's do this, Na versus Fe, 3+. So let's look at these cations' parent bases. So the cation's parent base would be NaOH. We know sodium hydroxide is strong, right? No effect on that pH. This pH is going to be neutral at 7. Let's look at Fe. Its parent base would be FeOH, iron hydroxide. And we know that it is not strong. We'll call it weak. And so we know that when when this goes through hydrolysis, Fe3+, in H2O hydrolysis, and it forms FeOH3, it's making those acidic protons. So yes, this is making more acidic. And our question is asking us, which one will form the more acidic solution? Our iron nitrate will. Let's look at number 2, potassium bromide, so KBr, versus potassium hypobromite, KBRO. All right, so let's separate potassium bromide into its 2 ions. We've got K plus and Br minus. And here we have K plus and BrO minus. Now let's look at the parent base to K would be KOH. Same with here, parent base, KOH. And we know that KOH is strong. No effect on the pH. So now let's look at these anions. We've got BRO. The parent acid would be HBr, hydrobromic acid. We know that this is strong. No effect on the pH. That means that KBr is going to have a pH of 7.00. It's going to be neutral. Let's look at BRO. The parent acid would be HBRO. And if you weren't exactly sure if that's strong or weak acid, we can look on our Appendix D, hypobromous acid, and it has a Ka constant. So we can see that that is a weak acid. So what is that going to do to our acidity? Well, let's go back and look at the chemistry. If I take my BRO minus and it goes through hydrolysis, then it's going to form, this BRO is going to grab an H, HBRO, that's the parent acid that we just were talking about. And what are we left with? Our water just gave 1 proton away, so we're left with OH minus. So this is going to become more basic. Those hydroxide ions make this more basic. So we've got a 7.0 and we have basic. So which one is more acidic? our potassium bromide. Let's look at methylamine chloride or barium chloride, see who's more acidic. So methylamine, I think we just did that on the last slide, CH3NH3Cl, and barium chloride, BaCl. So we know that the parent, let's arrange this a little bit differently. The parent acid for Cl would be HCl. We know the hydrochloric acid is strong. So this is not going to have anything to, it's not going to change the pH at all. I'll just write strong, strong. All right, now let's look at the parent base to these two. We know that the parent base would be BaOH2, which is strong. So this is going to have a pH, again, it won't affect the pH, we'll have a pH of 7. Let's look at this one, CH3NH3. Its parent base is going to be CH3NH2. All right, now this is weak. And let's look at the chemistry. What happens when CH3NH3 goes through hydrolysis, H2O? That means it's going to lose that, it's going to make that parent base, CH3NH2, that we've just made up here, the parent base. So it lost one of those H's. That means that we have H3O plus. That means that this is going to be more acidic. So if we have a pH of 7 and we have one that's more acidic, it's going to be lower than 7. So therefore, this compound, our methylamine chloride, will be more acidic. And let's look at our last one. We have ammonium nitrite, so NH4NO2, versus ammonium nitrate, NH4NO3. So again, let's look at our parent acids, parent bases. The first one that sticks out to me is this NO3, because we know that its parent acid, HNO3, is strong. So it's not going to have any effect on that. Now, this parent base, NO3, ammonia, we know is weak. And we know that that's going to make this more acidic. Remember the chemistry, we've done that a few times now. One more time, when we have NH4, that's what we're starting with, and it goes through hydrolysis, it's going to form this parent base that we just wrote about, NO3. So it lost one of those H's, and it donated it to water, and so we have H3O plus, which makes this more acidic. So this compound is becoming more acidic. Let's look here. So I have our NH4, which we just said, the base is NO3. It's weak, it's making it more acidic. So I'm just going to copy everything we just did here and write down more acidic. Well, let's look at NO2. Its parent acid is HNO2, which is a weak acid, which is weak. So we know that when a weak acid, or when this NO2, let's look at the chemistry, NO2 minus, when it goes through hydrolysis, H2O, it's going to form that parent acid, HNO2. So therefore it's grabbing one of these H's, and what are we left with? OH minuses, hydroxide. So it's going to make, this will make it more basic. So this is interesting because this will make it more acidic, this will make it more basic. It's almost like they're counteracting each other. I'm not going to say that it's going to be neutral, but when I have this compound where it's purely making that more acidic, and we're asked which one of these is going to be more acidic, our ammonium nitrate will, for sure. All right, let's look at our last practice problem. Practice, practice, practice. That's how you're going to get this. So we want to predict whether the salt, sodium hydrogen phosphate, will form an acidic solution or a basic solution when dissolving in water. And it's telling us that it's amphoteric, so it can act as an acid or a base. So we're going to need to do both when we're solving this. So sodium hydrogen phosphate, NaHPO4. And this is -2, actually, so it's just Na2HPO4. Okay, so we know that the parent base of Na is NaOH. And we know that that is strong. And that means no effect on the pH. Well, let's look at HPO4. So it just told us that it's amphoteric. So HPO4 can act as an acid or a base. HPO4 as an acid. And we're going to look at HPO4 as a base. So let's say we undergo hydrolysis. So therefore, this water is acting as a base. So when it undergoes hydrolysis, my acid is going to donate its proton. So I'm going to have, oh, and this is a 2 minus, by the way, because of that 2 minus. There we go. So it donates that proton. So I'm left with PO4 3 minus, which is our phosphate. So this is our conjugate base. And so if it donated that proton, I'm left with H3O plus, acid, right? Good. Now in this case, let's look what our Ka constant is. And it should be on our appendix here. And we're going to look up the Ka constant for HPO4, which is phosphoric acid. Now phosphoric acid is a triprotic acid. So we know that to lose the first hydrogen, this is its Ka constant. The second hydrogen, and we're trying to pull off the third hydrogen. So our Ka constant to pull off that third hydrogen, which is what we just were doing, pulling off that last hydrogen, is 4.2 times 10 to the negative 13. Now let's do equation number 2. Looking at HPO4, 2 minus as a base. When that undergoes hydrolysis, so this water is acting as my acid. That means that this, if my acid is a donator, so this will become H2PO4 minus, this is my conjugate acid. And what am I going to be left with? OH minus. So again, we look at this and we go, ooh, well, it can produce, if this HPO4 acts as an acid, it will produce hydronium. If it acts as a base, it's producing these hydroxides, the conjugate base. But how do we know which one's stronger? Well, we need to find this K constant. In this case, though, we're going to be finding the Kb value. And how do we find the Kb value? Well, remember that expression that Kw is equal to Ka times Kb? So we know Kw is 1 times 10 to the negative 14th. We know our Ka value is 4.2 times 10 to the negative 13th. So our Kb value, if we plug this into our calculator, let's do 1 times 10 to the negative 14th divided by 4.2 times 10 to the negative 13th. We get a Kb value of 0.024. So remember that slide that said if the Kb value is greater than Ka, so here's our Ka, here's our Kb, which is a greater number, 0.024 or 4.2 times 10 to the negative 13th? Well, in this case, we have our Kb is much greater than Ka. So will it form an acidic solution or a basic solution? Definitely a basic solution. At this point, you have done a great job. You have finished with me looking at how Kas and Kbs are related. You have also practiced the hydrolysis of salts and using those values to start ranking pH of those negative and positive ions. This concludes the lesson. Your notepad is now filled down towards the bottom of the page.